Theories of reaction rates. Questions. Why does the rate of a reaction increase with increased concentrations of reactants? Why do increased temperature and surface area increase reaction rates? Collision theory and the rates of reactions. What causes a reaction to occur? A reaction occurs when two reactant particles collide with one another. This is the basis for collision theory. In order for a reaction to occur, reacting particles, atoms, molecules, or ions must collide with each other. What factors affect the rate of reactions? Number one, the concentration rate. If a collision is necessary for a reaction to occur, the rate of the reaction will increase if there are more collisions per unit time. More reactant particles in a given volume, that is, greater concentration, will increase the number of collisions between the particles per second. Surface area. Simple collision theory is used to explain why increasing the surface area of a solid phase reactant speeds up a reaction. With greater surface area, more collisions can occur. But note, not every collision between reactants results in a reaction. For a collision to be effective, it must satisfy both of these criteria. One, there has to be the correct orientation of the reactants, and two, there must be sufficient collision energy. So here is an example of the correct orientation of reactions. Given this diagram, collision geometry is the reacting particles must collide with the proper orientation relative to one another. Only one of these five possible orientations of NO and NO3 will lead to the formation of the product, and that would be the bottom one. Take a moment, see if you can see the difference in the orientation. Activation energy. The reactants must collide with energy that is sufficient to begin to break the bonds in the reactants and to begin to form the bonds in the products. This is called activation energy, E subscript A. The activation energy of a reaction is the minimal collision energy that is required for a successful reaction. If you plot the number of collisions in a substance at a given temperature against the kinetic energy of each collision, you will get a curve like the one shown here. The type of distribution that is shown by this curve is known as a Maxwell-Boltzmann distribution. The dotted line indicates the activation energy. The shaded part of the graph indicates the collisions of energy that is equal to or greater than the activation energy. 2. Activation energy. How does the distribution of kinetic energy change as the temperature of a substance increases? The distribution of kinetic energy is a sample of reacting gases at different temperatures, T1 and T2, where T2 is greater than T1. The activation energy is indicated by the dashed vertical line. Two observations are apparent from the graph. 1. At both temperatures, a relatively small fraction of collisions have sufficient kinetic energy, the activation energy, to result in a reaction. As the temperature of the sample increases, the fraction of collisions with sufficient energy to cause a reaction increases significantly. So now we have the transition state theory. The transition state theory is used to explain what happens when when molecules collide in a reaction by examining the transition or change from reactants to products. The kinetic energy of the reactants is transferred to potential energy as the reactants collide due to the law of conservation of energy. You can represent the increase in potential energy during a chemical reaction using a potential energy diagram, which is a diagram that charts the potential energy of a reaction against the progress of the reaction. The y-axis represents potential energy. The x-axis, labeled reaction progress, represents the progress of the reaction through time. So here's an example of a potential energy diagram. This is for an exothermic reaction. A potential energy diagram for an exothermic reaction is shown. The reactants at the beginning of the reaction are at a higher energy level than the product. The overall difference in potential energy is the entropy change in H. There is no way to predict the activation energy of a reaction from an entropy change. A highly exothermic reaction may be very slow because it has a high activation energy. Conversely, a reaction that is very fast might release very little heat. The entropy change of a reaction, then, is determined by finding the overall energy that is transferred. The activation energy of a reaction is determined by analyzing the reaction rate. A potential energy diagram for an endothermic reaction is: the reactants at the beginning of the reaction are at a lower energy level than the product. This is an endothermic reaction. The overall difference in potential energy between reactants and products is the entropy change. Transition state theory continued. How are the activation energies of forward and reverse reactions related? For an exothermic reaction, the activation energy of the reverse reaction, EA reverse, equals EA forward. As energy activation reverse equals energy activation forward, plus the change in H. For an endothermic reaction, the energy activation energy reverse equals the activation energy forward minus OH. So slides 9 and 10 show the activation energies of forward and reverse reactions. Some definitions: transition state, changeover point. The top of the activation energy barrier on a potential energy diagram represents the transition state or changeover point of the reaction. The activated complex is the chemical species that exists at the transition state. The activated complex is a transitional species that is neither product nor reactant. It has partial bonds and is highly unstable. So here is a sample. Consider the substitution reaction between the hydroxide OH- ion and methyl bromide BrCH3. Methanol CH3OH and a bromide Br- ion are formed. It includes several snapshots as the reaction proceeds. So we can see how the molecule is positioning itself, how it's bonding, and how it's driving according to our reaction progress and what's happening as the shape of the molecule changes. Take a moment to study this. So, the summary of the reaction: for a successful reaction to take place, BrCH3 and OH- must collide in a favorable orientation. The OH- ion must approach BrCH3 from the side that's opposite to the Br atom. When this occurs, a partial bond is formed between the O of the OH- ion and the C atom. Simultaneously, the CBr bond is weakened. In your next video, you're going to take a look at how to draw a potential energy diagram.